So, guys, thank you for coming after lunch. If you check the schedule, the title is slightly, no, it's not slightly different, it's completely different. But the topic is the same. I just changed the title because I was assuming that what I'm doing is really very simple and is really just that. So we are applying knowledge compilation techniques to the specific inference in graphical models required by causal inference. And more specifically, our focus is on counterfactual inference. To give you a bit more context, so this was the original title of my talk, and this is the title of a paper we recently wrote together. I'm Alessandro, I'm from IDSIA, which is a Swiss AI lab. I wrote together with my colleagues at IDSIA, Marco Zaffalon and David Huber, who is a student in our group. And this is a joint collaboration, joint work with the group of Adnan Darwish and Izuo Chen, he's the student of Adnan. And I think this sentence I stole from an old paper by the group of Darwish is kind of telling what we are trying to do. So knowledge compilation is basically trying to solve, in a general, in a stretched sense, to solve a complex problem, typically problems in higher complexity class with respect to NP. And what we are doing is considering a very challenging problem, which is the bounding of counterfactual queries in structural causal models. And we want to do that by means of knowledge compilation, by means of tractable circuits, basically. So this is what we did. As not everybody here is from AI, I'm spending a bit of time just saying something about general AI stuff. Actually, probably most of the people coming here at this moment is from AI, but let me still say something, give some context. Here are the dates. You can read are very, very approximate, but this is just to give a point about where we are. So, and this is also just to mention that what we are doing is completely in the field of the Pearl approach to causality. What we do is computing inference in structural causal models a la Pearl. Structural causal models, in a sense, are the evolution of Bayesian networks. So Bayesian networks have been proposed a long time ago. People start to focus on inference, on probabilistic inference in these associational, correlational models. Tractable circuits have been, from a certain perspective, proposed exactly to address inference in graphical models. In the meanwhile, research on causality based on graphical models go ahead. And what we are trying to do is to go back. So use these tools originally derived for Bayesian networks in the field of causal models. So this is somehow the setup. Of course, there's a lot of people working with probabilistic circuits. This community is part of them. But there are new relations between these approaches and causal analysis. Okay, this is not that important, but yesterday Cassio was emphasizing, and I totally agree with the big success of deep learning, I would say, in the last 10 years. But I'm very impressed also by the success of deep learning in the last year. So if you believe if you think what is happening with large language model and so on. This is amazing, no discussion, but a point of, again, Darwish and Pearlian, other people is that, okay, we are looking for intelligent system. What deep learning is doing is mostly elaborating a system for sensing. So we are very good, computer vision, we have very good speech recognition. What was not obvious, but we are realizing, is that we have also very good language models. So if human vision is a complicated function, deep learning is good in approximating this function. And this is true for speech recognition, and this seems to be true also for natural language processing, for what we call language. Maybe this is true for all the human activities. Maybe there is room still for reasoning techniques, for symbolic approaches that need to be used to really achieve intelligent behavior. And this is especially true for causal analysis. And if you are familiar with many comments, many books, many papers of Judea Pearl, you probably read this kind of sentences about the importance of the causal meaning, in the sense that we should be ambitious, we should capture correlation, but we can do more. And this picture is also from the book of Pearl. It's the so-called ladder of causation. I think it's nice. It's more than that. There is also a formal characterization provided especially by Elias Barenboim. It's like the 3 different levels. And if you want, machine learning is here. Machine learning is about some machine learning, about finding very good correlation and doing very good prediction based on a correlation. Reinforcement learning is one level up in the sense that it's about computing the effect of an intervention, of an action. So it's the reasoning provided that we did something. But even more challenging, and the focus of my talk, is on counterfactual reasoning, where we kind of distinguish between the real world where we observed something and an hypothetical alternative world where we did a different action. So we have room for a contradiction between the action, the state of the variable in the real world, and the state of the variable after an intervention in an alternative world. So this is what counterfactuals are about. Okay, here I'm trying just to say that these 3 different levels correspond also to different levels of complexity from a probabilistic graphical model perspective. So an observational query, we can say we have observational data, empirical data, we learn a Bayesian network, and we just compute a single inference to answer an observational query, updating or whatever. Say that we are interested in intervention, say that there is a special class of interventional queries that can be somehow reduced to standard queries in a Bayesian network, which are the so-called identifiable queries. Do calculus, parallel do calculus is a graphical approach is about that. Say that the query can be reduced to a number of observational queries. So you can do this kind of computation, and basically you can run multiple Bayesian network inference or whatever, and obtain the result of the intervention. Counterfactuals, generally speaking, are even much more challenging in the sense that, in general, counterfactuals are only partially identifiable. Is that you cannot exactly compute the probability associated to a counterfactual, you can only bound the counterfactual. And if you are required to compute a finite, sometimes very high number of inference in the graphical model, here is like an optimization problem over a continuous domain. And generally, we can prove that this is NPPR, just to say that it's a more complex task. And we are focused on this task, on bounding the counterfactual query, on computing the bounds of this interval. Okay, just let me say that in this area, do calculus is a possible approach, but because of do calculus, you have to compute multiple inference in the Bayesian network. The group of Rina Dechter recently is working in this direction, but from an alternative perspective, and is trying to use EM to compute also the probability over the variables that are not in the data set, and basically to compute by a single query the answer if you want. A lot of people, not especially, but of course our group, but also other people is trying to compute the bounds of counterfactual queries. We initially did something in the field of Creedal network. I'm saying something about that. Then we moved to EM approaches. Some other people like Elias, these are, let's say, the leader, the main leader is not, there are lots of authors in this paper, but this is the group of Elias Barenboim who is trying to do this approach based on sampling. Some other people is doing polynomial programming to solve this optimization task. We are trying, and this talk is about doing this EM, but together with knowledge compilation. So this is just to have some framework. I know some of you is very into causal models, but let me say some background. Let me use a very trivial, one univariate example. Useless, but just to define the language. So we have a variable we can observe. We call this endogenous variable. And let's say we have data. We have a set of observation about this data. So we do some statistical learning, and we learn a distribution over the endogenous variables. But we assume that this variable has been, let's say, determined by a latent variable. We call this variable exogenous. And there is a structural equation determining the state of the endogenous variable from the exogenous one. Okay, So basically, every state of U determines the corresponding state of X. In this example, I have 4 states for U and 2 states for X, and this is the equation, whatever. And uncertainty on the latent variable propagates and becomes uncertainty on the endogenous variable. So basically, what we observe is this. But if we assume that X is produced by a latent variable, this probability should coincide with this probability. If we have a distribution over U, we can compute the corresponding distribution over X. But in practice, we have the distribution over X, and we have to go back, invert the relation, and compute the distribution over U, because it's what we eventually need to compute the causal queries. But this mapping is not one-to-one. Generally speaking, we cannot invert this mapping. And so if we go back from X to U, we will obtain a set of so-called consistent with the empirical knowledge distribution over the latent variable, over the exogenous variable. And that's why queries like the counterfactuals are only bounded, are so-called partially identifiable, because we have different values of P of U giving different output to the query. And so the result of the query is only bounded. There is no way that one of these specifications is more exact than another one. The bounds are not errors. The bounds are intrinsic. Please.
What is the delta F U X?
Sorry?
What is the delta?
That is Kronecker delta. So actually, this is total probability theorem. So this is the conditional probability. As we have an equation, the probability is 1, where X is equal to the output of the structural equation and 0 otherwise. So it's 1 if they are equal and 0 otherwise. The Kronecker delta. Okay. So no, I think this is an interesting point, because it's just to say that this is a conditional probability. In Bayesian networks, we are required to quantify this conditional probability. This is a Bayesian network, if you want, but it's a special Bayesian network, because this conditional probability table is degenerate. The columns are made only of 0 and 1s. And this is something we are going to exploit during the knowledge compilation process. Okay.
Do you assume that you know F?
Sorry? Yeah, it can be discussed. Let me give me a second, but it can be discussed. But initially, I'm assuming it's a good point, of course. Okay, this is just the general case, which is the real case, because we never use models based on single variables. And okay, generally speaking, we have a collection of endogenous and a collection of exogenous variable, a collection of equations. Typically, we assume that the latent variable are the root of the graph. This is so-called the semi-Markovianity assumption. But let me be quick on that. So you might see a stronger relation with Bayesian networks. And actually, from a certain point of view, a structural causal model à la Perle is just a Bayesian network. It's just a Bayesian network with very special conditional probability table, with deterministic conditional probability tables implementing the structural equations. Okay. This assuming that everything is specified, and this is what I call a fully specified structural causal model. But in practice, we might, a critical point are the structural equation, but let's for the moment assume that we have the structural equation. The second point is that these are the marginal over the root nodes, which are exogenous, which are latent, and generally speaking, we don't have this distribution. So the problem, again, is to invert the mapping. We have the endogenous observation, and we should go back. But when we go back, we have a multi-valued specification of the P of U. So this is the setup. So it's more complicated. But we generally, in a real scenario, we have to cope with only partially specified structural causal model. Okay, I'm assuming that we have the equation, but let's say that we don't have the equation. If we don't have an equation, we can consider a conservative approach. Let me use this example. So we have a Boolean variable and Boolean variable. And these are endogenous. These are observable. And we have a latent exogenous parent. For each value of U, the relation between X and Y should be deterministic. So in a sense, the role of U is just to index the possible deterministic relations between X and Y. say we have two Boolean variables, we only have 4 possible deterministic relation. Y can be always 0, Y can be always 1, Y can be X, and Y can be not X. So we have 4 mechanisms. And the role of U, we need 4 states. We don't need more than 4 states of U to enumerate all the 4 possible mechanisms. This is what we call the canonical specification of the structural equation. Of course, if the model has many parents, the number, the cardinality of U you need to enumerate all the possible mechanisms grows exponentially. So this can be an issue. But let's say, and let me also say that if you have some domain knowledge about the system, you typically discard some of the possible mechanism. Let's say that this is a disease, let's say this is COVID, and this is a COVID test. And let's say that for some reason, it doesn't make sense a test that always tells you that you have COVID. Maybe the test is broken, and it always says that you don't have COVID, but this one makes no sense for some reason. Or this will be the perfect test. This will be the anti-perfect test. So the test always telling you that if you're sick, you're not, and if you're not sick, you're sick. Maybe it makes no sense. So let's discard these 2 states. So we don't need 4 states, we need 2. And this is, okay, what we try to do to, let's say, to address the problem of the specification of the equation. So let's say for the moment that we have the structural equations. We have the endogenous data. We want to learn the latent. If the model is fully specified, we have the latent. So if the model is fully specified, we have a Bayesian network. So let's use Bayesian network inference. Exponential in the 3 width, and faster, it can be faster in the presence of context-specific independences, something that you don't see from the graph of the model, something you can see in the tables. And you can also take advantage of deterministic relations in your model. And knowledge compilation is very good because in some sense it's visualizing, it's explicitly producing smaller circuits in the presence of this kind of advantage of good, let's say, situation from the perspective. And especially determinism is very appealing from our perspective because our model are deterministic. The conditional probability tables are deterministic in structural causal model. And this is an interesting empirical test. If you take some random structural causal model, you run a knowledge compilation, you can see that even models with high 3 width are tractable. And the reason is determinism. The reason is that the compiler is taking advantage of the recurrent structure of the presence of this 0, 1 to make smaller circuits and then to have, let's say, tractable results. These are results from Bayesian networks forced to be deterministic or to have a context-specific independence. But the message is that if you have determinism, the compiler can take advantage out of it. And there is an interesting notion of causal 3 width. So is the 3 width taking into account that you have a structural causal model with a deterministic CPT. And this is, generally speaking, smaller. It can be equal, but smaller than the actual 3 width of the model. So this is explicitly showing the advantages of determinism in causal models when you run a knowledge compilation.
Can you compute it in advance? The causal 3 width, can you compute it?
No, no. This is operational, but you have to do that. Yeah. I think this is still open. This is Darvish stuff and so on. And let me also mention that we will use for this stuff standard compilers, which can be, general purpose compilers. This is I see from the group of UCLA. Maybe there is room to specialize this compiler to this structure. So maybe we can take further advantages of this structure. It's one of the open questions from my perspective. Okay, this was assuming that the model is fully specified. If the model is not fully specified, so if we should go back to the P of U from the X to the U, okay, in some case we have this do calculus, so the query is identifiable, but generally speaking, we have to compute the bound. The task is challenging, and it can be proved that it's equivalent to this Creedal network, to this generalized Bayesian network. And this is another way to see why you need to compute bounds and not the sharp values for the query. In a sense, a partially specified structural causal model is just a collection of all the fully specified structural causal model that are compatible with the data, with empirical observation. And the bounds are computed with respect to this collection of models. Okay, here I think I can not skip, but just be very quick on that. Is just to showing the mapping we derived between these models and Creedal networks, which is not necessarily operational, but it's just to show you an explicit formulation of this set of compatible structural causal model. So if you want, this is the compatibility constraints. This is a model with 4 endogenous variables. The U are the latent variables. These are the equations. And this is just the joint probability of the Bayesian network. The delta are the conditional probability tables. These are the probability of the root nodes. We marginalize the latent variable, and the result should be the empirical model. This is already the constraint of compatibility. But this constraint is global, it's involving all the variables together, and it's nonlinear. What we can do, please?
Are the latent variables, are they considered to be independent?
Yeah, because this is a semi-Markovianity assumption. So they are root variables, and so for the semantic of directed graphs, they are dependent. So the joint probability of the U is the product of this probability.
Can I have the same variable being input to multiple?
Yes. This is what we call a Markovian model, but there are no model Markovian where the U is a parent of multiple, is a confounder between 2 or more variables, of course. And in fact, let me show you the mapping. The mapping basically is reducing these global and nonlinear constraints with respect to the P of U to a collection of local, one separate constraint for each latent variable, and a linear constraints. So we decompose the global constraints into linear one, and this gives you a proper Creedal network specification. In the Markovian case, which is the case where you have a single U for each variable, this is trivial. In the case of confounder, it's still doable, is what we do. The problem is what we have a parent with multiple latent parents. A variable, an endogenous variable with multiple latent parents. This is more tricky. And that's why basically, okay, we do inference. We can use Creedal network inference algorithms to solve causal inference, but that's why this is something we did like 2 years ago. And at some point, we realized that we should do more. This is for a standard interventional query. You do what Pearl called the surgery on the model, and then reduce the query to a standard query in the graphical model. For counterfactual, you have to duplicate the endogenous variable because you have the actual word and the alternative word. Some people call this a twin network. Let me go faster. And basically, after this Creedal network approach, which is still important to understand what is the problem, the shape of the problem, we have the problem of practically compute these Creedal sets, these sets of distribution, and then the bounds of the query. And so we consider an EM approach. Why we consider an EM approach? Because the latent variables are missing. By definition, they cannot be observed. So they are missing at random. So we are in a setup for running the EM algorithm. And this is basically what I will detail a bit this algorithm, but this is basically what we can do. The point is that as there are multiple P of U, this is kind of trivial. We just do the expectation over the different, by computing the query for all the elements in the data set, and then the maximization, we compute the new probability. And we do that in an iterative way. If you are familiar with EM, this is really a trivial example of EM. The EM go to a stationary point of the likelihood. You can prove this important fact. So the fact that if the output of the EM is the global maximum, and you know what the global maximum is, because the global maximum is basically the likelihood of the empirical model. If you get the global maximum, you are getting a point of the Creedal set. So you can use the point returned by the EM to compute the causal inference. And by doing that iteratively for multiple initialization of the EM, you obtain an inner approximation of this interval-valued query. This is the idea. I'm not entering the detail. We have credible intervals, and in practice, we can compute a very good inner approximation with a relatively low number of initialization, of different initializations. This is the algorithm, and my focus is here. This is the expectation step, and we need to compute inference after the initialization of the parameters. We have to compute inference in a fully specified structural causal model. This is a Bayesian network inference if you want, but we have to compute lots of these inference. And we also want to compute the likelihood, which is the stopping condition. So we stop when the likelihood achieve a maximum. And this is something we want to make faster. And this is where, let's say, knowledge compilation comes into the play. So to make faster this EM approach, first of all, we can notice that there is a lot of room for parallelization. We're running multiple initializations, so all the initialization can be executed in parallel. We have to compute the inference over the posterior inference for each latent variable over the records in the data set. So this can be done in parallel, and there is a further level of parallelization at the level of the so-called C component of the model. But what is even more important for us, we want to do knowledge compilation to have a faster inference on these Bayesian networks, if you want. But we have a lot of different models, because every time we have a different initialization, the EM is an iterative approach. Every time we have a different initialization, a different iteration with different parameters. So all these Bayesian networks are different. So it seems that we need to recompile the model every time, which is demanding from a computational point of view. But, and this is the point basically of this work, we have to run a lot of inference in different models, but all these models share the same graph, they have the same variables, and they have the same equations. So the compilation process can be done somehow at a symbolic level. Maybe parameterized is a better word, but initially we use the symbolic. Let me explain this by this example. Okay, this is a Bayesian network. It's not a structural causal model. This is the Bayesian network. Let's say that the distribution on this root node is not specified, is symbolic. This is the compiled model. These numbers 0, 2, 0, 8 are here, but even the parameters P of A and P of B are here and here. Of course, we are not adapting this software to process this kind of symbolic computation, compilation explicitly. We just specify for all the parameters that we want to regard as a parameter, some random number, unique random numbers, and then we have a kind of hash. So we know that this number corresponds to this position, that this number corresponds to this position. If we have to change, let's say, if we have to produce the circuit for a different specification of this model, we just change the value of this parameter directly in the circuit. So we don't have to re-execute the compilation process. It's a very simple idea, but in practice, we save a lot of time because we do a single compilation instead of a lot of compilations. So this is our point. We did some preliminary experiment. Of course, you see that this is the compared to the standard model. If you do parallelization, you reduce the time by a factor of 2. If you do the symbolic compilation, you reduce the execution time by a factor of 5. And overall, we save an order of magnitude. But these are very preliminary experiments. The parallelization, you can do much more with parallelization. And we intend to improve a lot this compilation part. So this is the general idea. I'm about to finish. Okay, let's say in this way, anyway, I think that we are writing an extended version of this paper. We want to claim that we are, let's say, the state of the art for the computation of these bounds with regard to existing methods. What about the future work? We need, we are using general purpose compilation algorithm, basically this ACE of Darvish. Maybe there is something ad hoc for the canonical. The canonical is all the possible mechanism, if you remember, between a set of variables. Maybe you first order guys, you have some first order circuit that can implement in a more compact way this kind of relation. There are, connected component. Basically, we do a single compilation on the whole model. But we have a kind of decomposition of the model. So ideally, we would like to do the compilation separately for each component and then merge the result. This probably can be done. This is not complicated. This for me is complicated. This also might be complicated because we have this twin network with a different replica of the endogenous variable for each word. Maybe you can do some lifted inference. Also, what we are doing, and on purpose, is a query agnostic approach. So we do the compilation, and then, depending on the query we run, maybe we can do something specific for the query. So there is a lot we can do. Also, the EM, we propagate single values. Maybe we can propagate all the initialization together in this clearer sense, but this is more complicated. And of course, we have to do a better implementation of the parallelisation. We plan to use Julia, which is probably a better choice for that. That's it. Maybe I'm in time. Thank you, guys, for your time.
Do we have questions?
Okay, yes. Very nice talk, thank you. I have a general question and a more specific one. The general question is many of the methods that you are proposing in here are applicable outside causality. Namely, we always had Bayesian network and learning Bayesian network with EM and how to do it efficiently. So many of the ideas, especially compilation that you are proposing, are applicable in the general case. So that's just a statement.
Yeah.
And
I would say that
yeah.
We just specialized this idea to this.
Yeah, so it's applicable in general. But my question is about your assumption. You assume that the functions are known in this setup. Normally, the assumption is that the functions are not known. How do you do? Can you use the idea of compilation also that you compiled once, also when the functions are not known?
I don't know. I can tell you what we are trying to do. We are trying to do to assume that the function are not given, the cardinality of the latent variable are given, and we are trying to learn by EM-like approaches the best equations. Once we have the equation, we will go for the compilation. Not sure if you suggest to do the two steps together. At this stage, we are splitting the task. So first, we assume that we have the cardinality, and we learn by standard techniques with the EM the best reduced equation, and then we go for compilation.
Yeah. Can I follow up? Okay. One thing that you are arguing is that the compilation is very good in this case because we have functions. So this is just an observation. You can map any Bayesian network to one where you have these functions that you restrict yourself to functions with these hidden variables. So while I agree with you that if it's you have functions, I mean, compilation is likely to be good, but the idea that any Bayesian network can be expressed in this. So yeah, so there is this is a counter argument that the compilation will have the usual limitations. Sometimes it will be good, sometimes it regular or other methods for inference can be equally good. So this is just an observation.
I see. But maybe you can say that, of course, to achieve that, so to map the Bayesian network to a structural causal model, you need additional variables, you need more, let's say.
Yeah, the hidden, you will need to add hidden variables and the number, I mean, to model with the hidden variables, the probabilities that you have.
Okay, thank you.
Any other questions? Okay, so let's thank the speaker once more.